Thanks everyone for coming back. Not running away. We'll hear from Maria about one-form symmetry versus large N QCD. So until 5 past.
Okay, great. So hi everybody, I'm Maria Neuzil, and the organizer putting on a nice conference for us here. So I'm going to be talking about one-form symmetry versus large N QCD, which is based on this paper with Alexei and Theo Jacobson. So first, some very general background information to get us oriented here. So a lot of the things that we know about QCD come from studying its symmetries. But of course, we obviously don't know everything that there is to know about QCD. So it's nice to have some way to make approximations to get a handle on the theory. And a standard way to do this is to approximate n equals 3 color QCD by setting n to infinity. And in this limit, we actually get more symmetries, so we want to identify them, study them, and see what they can tell us about the theory. And in particular for this talk, I'm going to be focusing on the relationship between symmetries and selection rules, which are those nice exact statements that some expectation value of an operator vanishes exactly. So from our theorist's perspective, usually we probably think about this as saying if we have a symmetry, this must imply some selection rules as the consequence of that symmetry. Whereas an experimentalist might think about it in the opposite direction. If they observe that there's some selection rules in a process that doesn't happen, they might say, oh, aha, this is because there was a symmetry there to explain it. But is it always so? They both go back and forth. And in this talk, I'm going to look at a case in large N QCD where there seems to be selection rules without any apparent symmetry explanation. So first, I'll do some background information to get you the idea about why we're thinking about one-form symmetries in large N QCD in the first place. And then I'll go into some more details about how this plays out. So just a brief reminder of Wilson loops and their selection rules. This is just a typical expression for a Wilson loop built out of an SUN gauge field in the fundamental representation. And the way that we want to think about this here is as the world line of a quark-anti-quark pair. So we can imagine this pair being produced out of the vacuum, existing for some time, meeting and annihilating. The path that that traces out is precisely the Wilson loop. And here the statement of a selection rule for a Wilson loop is the statement about how the Wilson loop behaves in the limit that the size gets large. So specifically, it's this expression here where the Wilson loop vanishes exponentially with the area of the loop, and we refer to this as an area law. And now if we think about this Wilson loop, again, from the perspective of the quark-anti-quark pair, if it is exponentially unlikely that if it's exponentially suppressed that we can get these larger and larger Wilson loops, it basically means that the process of taking a quark-anti-quark and trying to separate them arbitrarily far is costing infinite amount of energy. And this is precisely a statement of confinement. So that's a very nice interpretation of these selection rules for Wilson loops. And as I mentioned, we're going to be looking at the large N limit of QCD. And this is actually a reasonable first approximation. And there are some ways that this that QCD simplifies in this limit. So one is that there's this common lore that says quark loops are suppressed for observables in large N QCD. And in this sense, we can say that harmonic observables in large N QCD basically recover their pure Yang-Mills expectation values. And in fact, this can be used to explain the behavior of Wilson loops in large N QCD. Basically, we see this sort of area law behavior, and then there's some one-over-n corrections that go away as we send n to infinity, and we recover the pure area law of pure Yang-Mills theory. So in this sense, we see the same selection rules for Wilson loops in Yang-Mills and large N QCD. And because of this, we want to look for a symmetry explanation for this behavior of these Wilson loops. And in order to do that, we have to discuss the concept of one-form symmetries. And this is understood. Yeah, go ahead. Yeah, so there's going to be some perimeter law term, but there's also a 1/n correction to the area as well. But we'll send n to infinity before we take the large area limit. Yeah. Okay. So we all know the usual way of thinking about symmetries, which is the invariance of the action or partition function under some group transformation of fields. But of course, there's this modern perspective in the last decade or so as symmetries being the presence of certain topological operators in the theory. And specifically for this talk, the generalization that we're interested in is the fact that symmetries can act on line operators, and we call these one-form symmetries. So I'll just briefly remind you of how this goes in pure Yang-Mills theory. So pure Yang-Mills has a Zn one-form symmetry, and these are generated by codimension 2 topological operators. And I'll call these topological operators U, and they're going to be labeled K, which is some Zn label to tell us which operator we're looking at. And of course, because it's a Zn symmetry, they obey a Zn fusion rule here. And for the expectation values of these symmetry generators, it's just simple. We just get one when the manifold is contractible. And when we say that this generates a one-form symmetry, we can look at the way that this acts on Wilson loops, which are the charged operators of this one-form symmetry. So here I've drawn a simple picture in 1+1 dimensions, but you can do this in higher dimensions as well. So I've put the symmetry generator inside the Wilson loop, and then you can imagine dragging this topological operator across the Wilson loop, and in doing so, you pick up this Zn phase, which is precisely the action of the one-form symmetry on the Wilson loops. And so this sort of manipulation can lead you to deduce selection rules for Wilson loops and Yang-Mills. You can get the area law by doing this sort of procedure. Okay, so to summarize where we're at so far, we know that large N QCD is similar to pure Yang-Mills theory in a couple ways. One is this common rule where the fork loops are suppressed, so we should somehow recover Yang-Mills theory in this limit. And both theories we saw have selection rules for Wilson loops. Now, as I also just explained, Yang-Mills has a Zn one-form symmetry, which explains the Wilson loop selection rules very nicely. So the expectation might be that large N QCD also has a one-form symmetry to explain the selection rules in exactly the same way that we got in Yang-Mills. Yeah, go ahead.
What is the crossover scale in large N QCD for area law to go to perimeter law? What is the scale with that? Is it log n?
Yes, it's log.
Log n.
The size of it.
I think it's actually quite hard to estimate. I'm not sure that it's long, but I think that's a discussion that we have to discuss.
That's what we get.
If you naively compare, yeah, we should probably explain it. It's a little bit subtle. I know the argument, but actually it's subtle. I suspect it might go like n to the first.
Thank you.
Okay. All right, so we have all of these nice expectations that make it really tempting to say that there should be a one-form symmetry in large N QCD. That seems like the conclusion. Yeah, go ahead.
Just clarifying this to make sure I follow. So you're saying this selection rule, like it's approximate, right? With 1 over n. So should we ask one form symmetry is also approximate 1 over n, or do you want to mix that?
Right. So ideally, we would be looking for something that has operators, symmetry generators that are topological up to 1 over n corrections. That would be the expectation. Yeah. Yeah. And I'll be more precise about what I mean by emergent one-form symmetry later. So now this gets to the details about why we don't actually see one-form symmetry in large N QCD, despite all of the nice intuition that we have. Okay, so if we're going to be discussing an emergent one-form symmetry in large N QCD, we have to be a bit careful about what exactly we mean in the limit that n goes to infinity. So for a usual symmetry, we have some topological operators, we have some charged operators that they act on, and we just think about all of them, and that's the content of our symmetry. But here, when we set n to infinity, we're going to have a lot of operators, and not all of them are going to remain non-trivial in the large n limit. So basically, we want to consider the topological, like the symmetry generators that remain non-trivial in this limit, and we also want to think about the non-trivial charged operators, the Wilson loops, in this limit. And here's a slightly more general expression for the way that these one-form symmetries act on arbitrary representation Wilson loops. So here, this symmetry action is still just a Zn phase, but now there's two things in the exponent there. One is k, which is still just that label for the symmetry generator that we chose. And the other thing is this nr, which is the anality of the representation r. So this is just the number of boxes minus anti-boxes in the Young diagram for the representation of this Wilson loop. So basically, we can think about this as the Wilson loop representations falling into these n different classes labeled by the anality of the representation. That's basically the charge under this symmetry. So we need to determine two things: which Wilson loops remain non-trivial at large n, and which UK symmetry generators still act non-trivially on those Wilson loops at large n. Okay. So a fact about Wilson loops in different representations is that the string tensions scale with the anality of the representation. So basically the string tension in some representation R scales with the anality times the string tension in the fundamental representation. So what this means is that if we take Wilson loops in these like large representations where the anality is scaling with n, these Wilson loops are going to be exponentially suppressed in the large n limit. So these are not the Wilson loops that we're interested in when we're discussing the one-form symmetry. So instead we want to take Wilson loops that have these small representations with some anality that's just a finite integer.
Sorry, you're thinking of small anality compared to n?
That's right. Yeah.
Fundamental.
But even that is like if you put a joint, it really depends how you do it, right? Because the adjoint is fundamental, anti-fundamental, its anality is 0. So
there might
naively the string tension is 0, but then if you factorize it, I mean,
there might
so
be
you have to
more
be.
symmetry. There might be more symmetry. We're interested in finding the invertible symmetries first.
Yes. So
At the very least, we have to consider the Wilson loops with small anality representations.
yeah.
And even with that, we'll get contradictions. Okay, so now that we're considering these small anality Wilson loops, we have to look at which topological operators would act non-trivially on those. So if we take, for example, a fundamental Wilson loop, which has anality 1, we get the usual z n phase from the action of the symmetry. But we observe that this phase is going to be trivial in the large n limit unless phase also scales with n. So that means that the non-trivial symmetry generators also must have k scaling with n. Okay, so to summarize, we know which Wilson loops we need to consider. We know which symmetry generators act non-trivially on them. And with this understanding of what we mean by emergent one-form symmetry, it turns out that large N QCD does not have this emergent one-form symmetry. So the two things that we need to check are those non-trivial Wilson loops. This part goes through just fine. For example, the fundamental Wilson loop is totally fine at large N. But the thing that's going to fail is how these symmetry generators behave at large N. This goes wrong. And there's a couple arguments I'll give for this. One is something called the endability argument. And then I'll discuss quark loop suppression a bit and discuss some concrete results from a last calculation.
So you're thinking of the analytic to be small and order 1.
Yeah.
But you could also think of it as being small with respect to n, but order n.
Right, like a small
A small fraction
small
of n.
mod, yeah.
So would that change the story?
Yeah, if you go back a few slides, those Wilson loops and expectation values go to 0 exponentially. But so we don't want to do that. At least it gets very subtle. Sorry.
Okay. Okay, so the first argument is called the endability argument. So in order to do this, we're going to assume for now that large N QCD does have a one-form symmetry and see what goes wrong. So if it does have a one-form symmetry, it has these corresponding topological operators. Fine. But another fact about large N QCD is that open line operators are allowed in this limit. So this is basically just a Wilson loop that ends on quarks. This survives in the large N limit. So these open lines are going to give us a contradiction with the assumption that the operators were topological. This is called the endability argument.
But did they survive in the large N
The open Wilson lines.
limit?
They do. We later on show a concrete calculation that we did in 1+1 to show that this is true. But
Compared to the closed ones, they are not suppressed.
right, as long as you're still taking small anality open lines. Yeah. Okay. So this argument can be done entirely with pictures, very simply. Again, I've drawn it in 1+1 dimensions, but you can do it in higher dimensions. What I'm going to do is evaluate this correlation function 2 different ways and come to a contradiction. So here we have our open Wilson line, and then we have the operator that we're assuming for now is topological. I can evaluate this by dragging this operator across the Wilson loop, and then picking up the usual Zn phase, that's the action of the symmetry. But on the other hand, since the line ends, I can take this operator and drag it over the top, and I can reach the same final configuration without picking up a phase. So from here we can conclude that,
Question.
Yeah.
It seems like for this case you've plucked a quark anti-quark pair out of the vacuum you're holding the pair by hand. And then is that a fair way of saying it? That's what this open Wilson line is.
It's still allowed dynamically as well, but
It's precisely these things that are suppressed from 1 over n dynamic.
the effects of quark loops on, so the expectation values of gluonic observables have quark loops suppressed, but this observable itself is not purely gluonic, so it still exists, but the effect of quark loops on this observable are suppressed.
I mean, I think the question is, do you work at the level of the sphere or the disk? Or, I mean, when you say large n, it's not about large n, it's not about really large n number, it's about the topology. So when you say, I don't know where you stop in the large n expansion. Do you include the disk or because the sphere is by definition just pure blue. So I think that's actually, is it what you're asking, that she incorporates effects of the disk?
I think this is making it too complicated. This is just QCD, and I can put an operator insertion. I'm allowed to study. What's the problem? Why do we need to bring in anything more?
No, you think about it.
You guys are finding a paradox, so.
Oh, the paradox appears also without considering open sometimes it's just a fast way to diagnose it.
Okay.
Okay, so using that sort of picture argument, we conclude that the expectation value of an open Wilson line is equal to itself times a phase, and this can be consistent in 2 ways. One is that this expectation value vanishes, but this doesn't happen even at large n, and I'll show a concrete calculation of that later. So that escape fails. The other way that this expression can be consistent is if this phase becomes trivial at large n, but as we discussed, we need to consider those symmetry generators with k scaling as n, precisely so this phase is not trivial. So we've arrived at a contradiction, and thus the original assumption that the operator was topological is incorrect. So the presence of these topological operators just really have a problem when you have these open Wilson lines in the theory. So with this definition, there's no one-form symmetry in large N QCD. But again, this is just an argument by pictures. Yeah, go ahead.
So just a terms, so usually when I think of the, if I can add the string, like an open segment of the string, so usually wouldn't we argue that implies perimeter law because I can break up my closed loop in a bunch of small strings? So where, what's the, which line, where does it grow from? You know what I mean?
So this is precisely why there's no area law at finite n, and then at large n that process is suppressed.
Breakup processes.
Okay. I see. So fusing those little segments into a closed loop is a suppressed process. I see. Thank you.
Okay. So again, this argument was just by pictures, so maybe you're not convinced, but we can do more.
So, sorry, so
Yeah.
you showed that there is no Zn one-form symmetry at large n. But you
Just-
also rule out that the small subgroup.
It was basically that it didn't really rely on precisely what this phase was, just the fact that the
But
operator.
in the next slide, you are assuming that k is over there. And
That's right. So from this argument, you can't exclude the fact that the small k topological operators are actually topological, but those are not the ones that we're interested in. So it's not enough. Yeah. Okay. So another way that you can argue.
I'm not sure exactly why k has to be order n. You can just renormalize everything by multiplying by n and subtracting some n piece. And even if k is of order 1.
What are you?
No, it's different.
What are you
Okay, it's n. It's not just true. It's like n winding of something. The k winding.
But you want to look at even the smallest generator of this transformation should survive, if anything survives.
No, but it might go to the identity operator. We're done. This is the issue.
Well, okay, never mind, we can check later. You can define Wilson loop -1 and then times n, everything. That's just the rescaled version. Because you're supposed to have a z generator, not a zn generator in large n of some sort. No.
We can resume this after. Okay, so here's a second argument that gives us a contradiction if we want to have a one-form symmetry at large n. So again, we had this nice intuition that there should be this quark loop suppression. You really expected to recover stuff that we know we have in Yang-Mills. So what went wrong here? And first, we can do this by considering a necessary condition for the one-form symmetry, which is that this UK operator converges to its Yang-Mills result at large n. That would be certainly something we would expect if this symmetry were to emerge. But it turns out this fails precisely for the operators which have k scaling with n. And we can again do this by contradiction. So first we assume that n suppression works as expected for take our symmetry generator that is labeled at 1. So this is like the smallest phase that we can consider. So assume that n suppression works as expected. This is just going to be the Yang-Mills value plus 1 over n correction. Then we consider a UK operator, and we can consider this UK operator as just a bunch of U1 operators on top of each other, basically. And so we can factorize this, plug in the assumption about the n suppression of the U1 operator, and at the end of the day, we get something that does not go to 1 as n goes to infinity. So basically, even if cork loop suppression works for this first symmetry generator, by the time you stack n of them on top of each other, this cork loop suppression goes away. So we see that this behavior is just inconsistent with expectations about cork loop suppression for these symmetry generators.
So this is thanks to the fact that k is scaling with that.
Exactly. Yeah, that's very important. Okay, and we can wrap it up by doing a few concrete calculations on the lattice. And we're going to do the simplest possible case, which is that we're going to check 2D QCD with scalar fundamental forks on the lattice. And I'll show you the results for two things. One is that we'll double check to make sure that these open Wilson lines really do survive in the large n limit, because that was very important for the endability argument. And then we'll also check the expectation values for these symmetry generators to see if we recover the expected Yang-Mills result as n goes to infinity. And this is going to fail. So briefly, I'll just flash some equations that show you basically how we set up these calculations. We can do them analytically by hand, pencil, and paper. We take our QCD action, which is just built out of the Yang-Mills part, and now including those fundamental scalars. And there's a very nice form of the action that we can use, which is called the heat kernel action. And this just makes it very easy to do explicit calculations in this setting. And we're going to do a hopping expansion, which is basically expanding in the kinetic term for the matter field. And when we do this, basically we're just pulling down these links order by order in the hopping expansion, and eventually we pull down enough of these links that we can build up tiny little Wilson loops and then progressively larger and larger Wilson loops at higher orders in the expansion. So basically at the end of the day, it means that this reduces to calculating expectation values of Wilson loops in pure Yang-Mills theory.
Are these fermions or scalars?
Scalars.
I thought you were, so you're also saying this is true for scalars?
Yes. Yeah, this is just the simplest
Okay.
example. Yeah.
Yeah, I guess it doesn't matter.
Yeah. Yeah. Okay. So there's a very nice way that we can write the symmetry generators of pure Yang-Mills theory. And it's basically just by taking some plaquette where we decide to insert our symmetry generator, and we just modify that plaquette by a phase, a Zn phase. And this definition is, you can easily check to see that it's topological, because you can just redefine link variables in the path integral, and this just shifts the defect along. And by doing this same procedure, you can also verify that this operator has the right correlation functions with Wilson loops. If you just shift it and move it outside of the Wilson loop, you'll pick up a Zn phase. So this is a nice expression for the operator that we are interested in.
Can I ask a simple question? Don't you generate, I mean, for scalars you can generate a mass, and it can happen that you emerge a one-form symmetry because of a very large mass. Isn't it n? I don't know, now counting eludes me, but
if
mass scale with n?
We want to keep the mass. We don't want the mass to get very large. If the mass gets very large, then that evades this argument.
But how do you control that for scalars? For fermions, you can set it to 0, and it's 0 because it's protected by chiral symmetry. But for scalars, you can't do that unless you I mean, maybe there's a large n counting. I don't know. Maybe it's suppressed by.
I'm not sure.
Never mind.
We'll talk about it later.
Okay. So once we have these this nice formulation on the lattice, we can go ahead and calculate a couple things. So as I promised, we checked the expectation value of an open Wilson line in QCD, and the result is this finite thing that is definitely not n suppressed. So this survives in the large n limit, and And the interpretation here is that these open Wilson lines are non-trivial, they survive, and they lead to the endability argument that I discussed earlier. Now the other thing that we checked was the expectation value of these symmetry generators once you put them into QCD. And you get this messy expression. But recall, we want to consider symmetry generators with k scaling as n. So for example, if you just plug in n over 2 to this, you get something that's exponentially suppressed in n. And this is definitely not going to 1, which is the result you would expect from pure Yang-Mills. So this operator does not converge to the expected Yang-Mills result, so it just does not have the correct properties to be a generator of a one-form symmetry. Okay, and that brings me.
Sorry, this is for any k or for?
What's that?
This is for any value of k or?
Yeah.
No, k is equal n over 2.
This is for any value of k, but specifically, yeah, this expression is generic for any value of k, but specifically we're interested in the large k. So, for example, if you plug in n over 2, that's what it's. Okay, so this is sort of the outlook. We see that large N QCD has these selection rules, the area law for Wilson loops, but it's not explained by any yet known symmetry. So there's two possibilities here. One is that there really just are selection rules with no symmetry explanation. This would be sort of disturbing based on our usual expectations about symmetry and selection rules. So if this is really true, we would want to know when exactly this can happen, so we can maybe find it in other contexts. On the other hand, a possible conclusion is that there's just some other kind of symmetry in large N QCD that does explain these selection rules, and we just don't know what it is yet. So it would be certainly very interesting to identify that and learn more about it. And that brings me to the end of my talk.
Especially for not going over time, you made my life much simpler.
Yeah, I want to understand what is the claim. It seems to me, please correct me, that what you're saying is essentially that the larger limit of 1 over n goes to 0 does not bring me to the n equals infinity, which I define as the theory that contains only the sphere partition function. Is that what you're saying, that the larger limit is actually singular?
I'm not sure how to understand your question. So you say.
So I define the infinite n theory as the theory that contains the partition function is the topology of the sphere. So it's a theory of Coulomb by definition. It's just a pure universe. And I think what you're saying is that if I increase n and 1 over n goes to 0, I don't arrive at that theory. Right?
You still, I mean, for example, you still have these open Wilson lines exist in that limit.
So I still want to understand. So there is a simple kind of similar story with the topological susceptibility. You would say QCD with massless quarks, the topological susceptibility is always 0. On the other end, the infinite n, the pure Yang-Mills theory, has non-zero topological susceptibility because theta is meaningful. So it seems to me that it's kind of a similar statement, but at least in that case, you know, like how to deal with the problem to make everything kind of make sense and smooth. I introduce a small mass to the quarks, and then the issue is whether I take first n to infinity or m to 0. There is this issue of m over n. So here I think that you can kind of make it smooth if you introduce a quark mass, and then the question is whether you first take the Wilson loop, the reduce first to infinity, then n to infinity, then m to 0. I mean, there are 3 quantities, and I think that the issue is really the order of how do you take the infrared regulator to 0, the large N limit, and the, I mean, so after giving this long speech, my question is, do you agree with me that it's a matter of limits?
Certainly the order of limits matters. Like even for just the expectation value of a Wilson loop, if you send the area to infinity before you send n to infinity, then you get problems with because the perimeter law term is not suppressed if you send the area first to infinity before you send n to infinity. So you definitely want to send n to infinity before.
How do you deal with the infrared regulator if you add masses? Because anyhow, in the last simulations, you added a mass. So, like, how do you deal with the limit of taking the mass to 0? Because it's an infrared cutoff.
Why are you taking the mass to 0 in this case? I understand why in the case, the interesting theory you described with data.
No. In that case as well, because weight because you produce quark loops that screen. So you want, now, you don't have control without actually, I mean, like all this work and stuff. You have to
This is
put a
taking too
cutoff.
long, Adi.
I know. It's a discussion now, becoming a discussion.
Any more questions? Questions, not comments. Well, at least short comments are cool. Okay, but is there a limitation why the open Wilson line has parameter law now?
Why the what, Wilson line?
The open Wilson line that you showed has a parameter law now instead of some kind of equal minus x squared.
Right. So the expression that I gave, you can write it in terms of a perimeter law. Sorry. Here, you can define Lex log of this as your string tension, basically.
Yeah, but somehow when you close the loop, right, you claim that you get area law.
Yes.
Right? When you say you open, you say it's perimeter law. Is there some simple way to understand why? Some intuitive. I could like move them around until it's almost closed. I don't know.
I think there's a difference when you close it. But I can give you an intuitive argument, or if you want to give the monitors of mesons.
No.
So an open Wilson line, you can think of it as this, like, don't make it long. You don't have to do that. It can be short. Just to get a feeling. And imagine that it's short. Then it's just a slightly screwed out meson operator. But the expectation values of meson operators suitably normalized do not vanish at order.
I'm not worried about the large counting. I'm worried about the power of x.
Okay, but then it's like a propagator for two ports. I mean, it's not.
So the fusion of an open Wilson line into a closed one is somehow very suppressed at large
Yeah,
n.
that has an extra n in it.
Yeah, the QQ bar. Is that right?
Yeah, that's right.
Joining the open one and then fusing the Q and the Q bar together, I think, is very unlikely. And so they're very different objects, I think. In this. Okay, these are just words. But
at the level of a hopping expansion calculation, like the difference is just very stark. But I don't know how to phrase it other than what people just said. It really matters what topology of the Wilson loop is.
Is this variable law meaningful in the sense that you could midpoint the Wilson lines that stretch between the two turning out some complement? Then this perimeter law just goes.
It just becomes one.
Yeah. So it's not. That is right?
so there's some discussion about a sort of crossover scale at scales like longer than that, like that's something that grows with n. And if I understand right, at scales longer than that, you really know you're not, it's not infinite n anymore. And at scales shorter than that, it behaves like the infinite n theory. Is there some way to argue that there's a proximate topological operator at scales smaller than this crossover scale?
Well, the operator is certainly not topological at finite n. And since you can see that it's also not topological at large n, I would imagine it's just.
Right. But yeah, I think topological is too strong. I want to have like some weak topologicalness where as long as you move it less distance than the crossover scale might be okay. But I think this is maybe not super well.
Yeah, because even without thinking about moving it, if it's just sitting there and you just calculate it all by
That's true. Fair enough. Yeah. No, you're right. Okay, thank you.
Okay, one more question.
I had a question on the dependability argument.
Yeah.
So I guess that obviously relies on having matter which sees the center of SUN, i.e. something with non-trivial anality.
Exactly.
You could imagine taking a limit where you have matter which has an anality, only matter with an anality divided n. So the endability argument would fail for a certain subgroup of Z n.
Yeah.
Could you cook up something like that and still have? Would that suggest that in the larger limit of such a weird model, you might still have some subgroup of Z or some one-form symmetry left over?
So you're just killing off. You're basically just like killing off some of the any phases that act on the lines that you're allowing get killed off, and everything else survives.
Yeah, well, just the endability argument would kill all of the symmetries in that case.
Because it would be a Wilson loop in some higher representation, not the smallest.
just preserve a subgroup of the ZM symmetry. Already find that out. And you can check here now, all the things that need to happen for that to make sense will go through. But it's already good.
Okay. Let's take a break, 20 minutes, so we meet at 1:30. The chairman will thank the speaker again. But
Zero tension.